Good morning, everybody. Welcome to our webinar. My name is Gordon Getty. I'm a Senior Application Engineer at Teledyne LeCroy, based in Santa Clara in California. And today we have a webinar on something that's a very new topic. It's about NVMe Management Interface Conformance Testing. So during the webinar today, I'm going to cover a couple of different topics. The first one, I'll do a short overview of the NVMe Management Interface, and then I'll talk a bit more detail about how you actually do compliance testing on this new technology. It's really great to see a large number of people sign up for the webinar, so this definitely shows a great interest in this topic. A little bit of background about Teledyne LeCroy for those of you who are not familiar with us. So we're one of the leaders in serial data test solutions. The company was founded, LeCroy was founded in 1964, the headquarters out in New York. And the Protocol Solutions Group, which is the one that's focused on testing the NVMe MI, was formed in 2004 when LeCroy acquired CATC. Our headquarters is here in Santa Clara in California. We acquired Catalyst in 2006, and this group specializes in protocol solutions for various different technologies, as you can see on the right-hand side there, with PCI Express, NVMe, Serial ATA, SCSI, USB, DDR, and so on. And NVMe MI is just a new one that we've added to this list. So what is the NVMe Management Interface? So it's a programming interface that allows out-of-band management of an NVMe or an NVM subsystem. So the NVMe Express Management Interface specification, I'm showing the 1.0 version there on the screen, was from 2015, and there's been a lot of work on this over the last year to year and a half in bringing it and actually implementing it into real devices. And now we're starting to see real devices appear for testing, and it's becoming an important time to start to do compliance testing and conformance testing to this specification. We'll talk a bit later about development of this specification as well. So NVMe Management Interface, this picture here is taken directly from the specification, and the comments here are a summary, but these are the key capabilities of the NVMe Management Interface. It's something that a technology that can discover devices that are present and learn the capabilities of each device. Now, this is in addition to the way a normal NVMe device would be detected. For example, an NVMe device would be a PCI Express device, which is obviously detected, but this is an additional management interface that can connect and manage devices within an NVM system. It becomes especially important when you have distributed or large server systems which have multiple devices, and being able to manage them within a system or remotely is very important. So other things that the management interface has defined are a standard format for the vital product data, or VPD, and also define mechanisms to read and write this data. So this is data that can be read from a device by a baseboard management controller in order to be able to determine the status, the health monitoring, for example, of a device. It can also store data about the environment and enabling the management controller to figure out the status later. So independent of the PCI Express links to the devices, the baseboard management controller can know exactly what the status of the system is. An example here, health and temperature monitoring. So if a drive fails in a system, then we can identify even if the system crashes or if the PCI Express link is broken. Another advantage of NVMe Management Interface is that there are multiple command slots. So long latency commands are prevented from blocking operations. So it's possible to issue multiple commands at the same time. The other advantage here is it's agnostic to the processor and operating system. So the management interface isn't necessarily working under Windows or Linux or the operating system on the server, but it can be managed remotely via a separate interface. So what I've tried to do in the presentation here is I note on the side which specification this is referring to, and a lot of this is taken, interpreted from the specification. So the NVMe Management Interface is used to send command messages which consist of standard NVMe admin commands that target a controller within the NVM subsystem. It can also be used to send commands that provide access to the PCI Express configuration space, I/O space, and memory space of a controller in the NVM subsystem, and also to send specific management interface commands that can be used for inventory or configuring or monitoring in the NVM subsystem. So these are different types of commands for different areas in the device. So it could be standard NVMe admin commands over the management interface. It could be PCI Express, for example, reading a configuration space register over the management interface rather than in-band through the PCI Express interface. And also specific management commands for the devices. You think, why would you want to be able to do this? Well, what happens if a PCI Express link goes down and I want to be able to read a PCI Express register from the device? Then I could do that via the management interface on a sideband interface. So NVMe Management Interface uses the concept of a management endpoint, so that's something that's on the device, and we'll see some illustration of that later. And management endpoints may support the same commands regardless of the physical medium used. So it's possible to have NVMe Management Interface either in band or out of band. So it could be in NVMe commands or it could be on a SM bus. We'll discuss this in a minute or two. So. Okay, here's just an example of what NVMe Management Interface can be used for. So this was a real customer example that I was told about. It can be used for controlling the fan control on the chassis based on temperature sensors inside the drives that are all connected to the SM bus, rather than just generic temperature sensors in the chassis. So the baseboard management controller can monitor all these different devices out of band from the data path and be able to make decisions on control of the fans in the chassis for cooling and then more accurately control that temperature. If you think about a server could contain many dozens of drives and it's much easier for a management interface to identify individual drives. It could be a simple thing like using the management interface to flash the LED on the front of the drive to identify which drive is failing if you had a failing drive. These failures, you can detect them and report them through a networked infrastructure of the baseboard management controller. So you have some remote access to the baseboard management controller operating system independently of the server operating system. So the management interface basically simplifies the identification and fault finding within a large storage system. So a little bit here about NVMe devices. So we start to see now both single port and dual port SSDs for NVMe. The single port device has a single PCI Express link. Typically at this point is a by 4 8 gig transfer per second link. A dual port device has 2 independent PCI Express links, but it's one drive, and these are typically 2 by 2 links at 8 gig transfer per second. Basically used for redundancy purposes. Now, if one or both of those links went down and you wanted to be able to identify what was happening with the drive without having some external interface, then you wouldn't be able to see that. But the drives are also coming with a SM bus or an I2C link, which can be used for management interface. And the diagram here shows on the left a single port device with a single PCI Express link. And then on the right we have a dual port device, but it has an EEPROM with the management endpoint controller connected to the SM bus connected to the system. So this is all going over the same PCI Express connector. There is an SM bus pin on that. This is just a diagram showing more what that looks like. So the topology would be you have the host with a host operating system and the baseboard management controller operating system. Then there's a PCI Express connector on the host connected to the PCI Express connector on the NVMe drive. And there is the SM bus connection between the two, but it's on the same connector. So this is just to clarify that there's not a separate wire connecting the drive to the host. It's actually on the same connector. But these two operating systems are separate. So the BMC operating system can talk to the drive independently of the host doing the data transfers. So again, this diagram is taken from the NVMe MI specification. For a single port device, there's an NVMe controller, which is the PCI Express function. It has the management endpoint that we talked about as well for the management interface, and that's controlling this particular NVM subsystem. In the case of a dual port device, then we could have multiple management endpoints on the same SM bus connection. In this case here, we have a single port, port 0. Actually, this is a dual port device. So port 0 is one PCI NVM subsystem, and port 1 is two PCI functions, but with also its own management endpoint. So this is again an example from the NVMe MI specification. So what about the vital product data? So NVMe Management Interface also defines a standard for the vital product data. And it makes this content available out of band from the PCI Express and the NVMe link. So it can be stored inside the NVM subsystem, and you could access it by NVMe commands, or you could have it on an EEPROM external to the actual NVMe device and connected to the SM bus. You could also have it as both, so it's not unusual to see devices that support NVMe MI over PCI Express vendor-defined messages or over the SM bus connection. So the vital product data should be accessible by any port that supports NVMe Management Interface, and it uses special VPD read and write management interface commands. So as we'll see later, those commands will be transported over MCTP. We'll see that in a moment. So we're talking here about in-band and out-band, in-band and out-of-band management. So there's different ways that a system can communicate with the NVM subsystem. So the NVMe driver can communicate with the NVMe controllers over PCI Express based on the NVMe specification. So there's NVMe admin commands which have a specific format and specific tasks that can be sent in-band using NVMe commands. The baseboard management controller has its own operating system, so it's independent of the NVMe driver and the host operating system. So these out-of-band paths are over MCTP, which is the transport layer for the NVMe Management Interface commands. Now the physical medium is different from that, so we'll see that in the diagram in a second, but the two different ways of transporting MCTP packets or messages is over PCI Express vendor-defined messages or over the SM bus connection, which is on the PCI Express or the U.2 connector. And just a note that the PCI Express vendor-defined message method is separate from the PCI Express traffic that is using the NVMe commands are using, even although they share the same actual physical connection. So this in-band and out-of-band also allows for security, for control and management interface to be independent of the data path. Okay, I have a couple of slides here just about MCTP. So what is MCTP? It's an integral part of the NVMe Management Interface, but MCTP itself is used for other technologies. It's used as a transport for the NVMe Management Interface commands. So NVMe Management Interface specification is moving towards the 1.0A. That's pretty close to being done, and incorporates several changes since the 1.0. We will be starting to do compliance testing for NVMe Management Interface at the first Plugfest, which is in May. It starts on May 22nd, and that's hosted at University of New Hampshire. It's going to be alongside the standard NVMe Plugfest, so that's going to be an interesting event to see how many NVMe Management Interface devices are going to be tested there. There will be an integrators list at this event, and the mandatory tests I'll talk about later in the presentation. So I mentioned there about MCTP, but I just want to cover here, this is something that I found a little bit confusing initially when I was trying to understand NVMe MI and MCTP and all the different specifications that are involved. So it's not a simple single specification for all parts to this technology. So NVMe MI has its own base specification. There's also binding specifications depending on the physical medium that's being used. So there's an NVMe MI to MCTP binding specification. Then there's the MCTP base specification. And then MCTP can be over either SMBus or PCI Express vendor-defined messages. So each of those has a binding specification. Obviously, the PCIe vendor-defined message binding specification applies to the PCI Express base specification, and then the SMBus binding specification applies to the SMBus specification. So these are all coming from different organizations as well. So NVMe MI specifications are coming from NVMe MI, MCTP comes from DTMF, and then PCI Express from PCI SIG and so on. So it's definitely interesting to get your head around which specification is used if you're trying to debug this technology, but it's important to know that each of these do exist. I'm going to talk a little bit about MCTP here in a sec. So maybe this illustration, this is from the NVMe MI specification, is a bit clearer. So at the highest level, we have the management application. So this could be a remote console, which is looking at the management controller, so either on the BMC or on the host processor. So this is the software that's controlling the NVMe Management Interface. The NVMe Management Interface sits on top of a transport protocol called MCTP, or Management Component Transport Protocol, and that in itself can be over SMBus or over PCI Express, and then each of those has its own binding specification. But the part we're looking at here is the green section, which has NVMe Management Interface. However, to get a link established, it must use either one of these physical mediums, and then the transport layer has to be established to be able to do any NVMe MI testing. It's a bit of a mouthful as well. Okay, so NVMe Management Interface messages, so this is at the green level here. These are request and response messages that are transported as MCTP messages with the message type set to be an NVMe management message over MCTP. And these MCTP types are specified in the MCTP ID and code specification. So that's another different specification. But really, for NVMe MI, it's relatively simple, just using this one type of command for the NVMe MI commands. So all of the commands originate with the management controller and result in a response message from the management endpoint. So this is at the NVMe MI level. If we go one level down, to be able to do these NVMe Management Interface commands, we need to be able to initialize and discover the MCTP devices. And this MCTP discovery occurs over the course of several discrete ordered sets. Now this is coming from the MCTP base specification. And as we'll see in the next few slides, some of this is actually defined by the physical media, but the concept has to be there in some form or other for each of those different types of media. So the first thing that's going to happen is a bus enumeration. There's going to be a bus address assignment. Then there'll be a discovery of the MCTP capabilities, an endpoint ID assignment at the MCTP level, and then the distribution and the use of routing information. So bear in mind here the MCTP specification is not specific to NVMe MI. That is one of the technologies that uses it. So the one thing to point out in the MCTP specification, it uses big endian byte ordering, while the NVMe specifications use little endian byte ordering. Just something to be aware of. And all the figures in the MCTP specification are illustrated with the little Indian byte ordering. This is just the representation, though. It doesn't change the way it is sent out on the physical layer, which is something to keep in mind. So bus enumeration, as I mentioned before, these are dependent on the physical medium that's being used. So that medium could be PCI Express or it could be SM bus. The enumeration of the devices on the physical bus is dependent on that particular technology, and the information on that is provided in the binding specification. So you can see on the right we have the NVMe or the MCTP base specification, and we have the MCTP PCIe VDM transport binding specification and SM bus I2C transport binding specifications. Those are quite a mouthful of a name for a specification, but these are the independent ones for each of the physical medium. So the MCTP endpoint requires to have a bus address that is unique to a given bus segment. So the bus address assignment section deals with the assignment of these addresses. Now some buses, such as PCI Express, they have built-in mechanisms. So when you plug in a PCI Express device, it gets enumerated with a bus and device and function number from the BIOS and the system. And that basically takes care of the address assignment for the PCI Express devices. For SM bus or I2C connection, these actually have some additional considerations because they're not specifically defined for MCTP or NVMe MI. So that's why we have this binding specification that says how should that be set up. For example, NVMe MI specification says that an SM bus device should have a default address of 3A. That only applies to the SM bus case. PCI Express would do it its own way when it gets enumerated by the BIOS as any other PCI Express device would. And as I mentioned before, because this is medium specific, the information is in the transport binding specification. It's not in the MCTP base specification. It's possible though that the NVMe MI specification calls out for specific conditions for MCTP or the binding specifications. So always check that out when you're trying to debug this technology. Okay, the next section I'm going to talk about is conformance testing. So we talked there about the NVMe Management Interface layer, we have the MCTP layer, we have the different binding specifications to the physical media. That all comes into play when we're trying to do NVMe conformance testing. So there is an NVMe Management Interface conformance test specification. This is getting close to being finished, and the tests which are going to be required for the Plugfest coming up in May are defined in this document. The document is originally written by the NVMe Management Interface Workgroup, and it's now being managed by the Interoperability and Compliance Committee, or the ICC, which is now an official workgroup itself. So they are responsible for defining the test specifications and organizing all the collateral for the Plugfest. So this NVMe Management Interface Conformance Test specification is the source of where the tests come from. And we'll go through what the tests are going to be in just a second. So there are 12 different groups of tests within this test specification. The first 3 are on MCTP, 4, 5, 6, and 7 are on NVMe Management Interface. And then 8, 9, 10, 11, 12 are some additional areas of testing that currently will be for information only. You'll see in a moment which parts of this will actually be a mandatory test. But these groups are based on the sections of the NVMe MI specification and the MCTP base specification. So inside this NVMe Management Interface Conformance Test specification, the tests are marked either as mandatory or informational. Now this applies to whether it's going to be included for the integrators list testing when the device gets tested at the Plugfest. So tests that are marked as mandatory will be required at this Plugfest if you want the device to be listed on the integrators list. Informational tests will also be run, and we will gather the results of those, and it is possible in the future that those tests become mandatory as well. So informational means the tests will be run, but it does not count towards the requirement for the integrators list. Okay, so as we talked about before, we have in-band and out-of-band. So NVMe Management Interface is independent of the physical transport, so the tests apply to both PCI Express, vendor-defined message, or SM bus paths. The NVMe testing, which would be considered in-band, is separate from the management interface testing, and that's a different set of tests entirely. What we're talking about here are the tests that are defined in the NVMe Management Interface specification. So the tests that are required as mandatory all come from the NVMe MI layer. The MCTP tests, while they're still valid tests, they're not mandated because this test specification was done by the NVMe Management Interface group. Although we will actually run the MCTP tests, which are required from a technical perspective, but will not be required from an integrators list perspective. So the mandatory tests are in groups 4, 5, 6, 7, and 8 from this test specification. Incidentally, if you want to get a hold of this test specification, it's currently held within the Interoperability and Compliance Committee. So to get a hold of that, you would either need to join that group or join the NVMe MI work group. Ultimately, this will be posted from UNH and will be sent out from there, as well as what's being required for the Plugfest that's coming up. So this is a list of the tests. So you can see these are all NVMe Management Interface tests. We're testing things like what happens if an invalid opcode is sent, what happens if there's a health status change, what happens if there's a message integrity check failure. These are the kind of things that we're testing. There's this complete list here. So this list is what's going to be tested at the upcoming Plugfest, and these are the tests that are marked as mandatory in the test specification at the moment. So if you want more details on each of these tests, if you get the test specification, that will actually tell you which specification reference it applies to and what the procedure is for each of the tests. So what kind of equipment do you need to do these tests? For the NVMe Management Interface Conformance tests, it's largely the same as you would use for NVMe testing or PCI Express testing, with a couple of extra details. So you need to use the Z316 exerciser. It needs to be the one with SM bus support if you're going to do the SM bus testing. You need to use a T34 analyzer. The T38 analyzer does not support the SM bus testing. You need a test platform also that has the SM bus support. It's marked on it whether it supports SM bus or not. And obviously an NVMe MI capable DUT. One other point here is that you do need to make sure you use the correct cable for the T34 to the test platform, and it has to be the one that includes the SM bus connection. And that's a blue cable rather than a black cable. So the test cases are all held in the software, so you can select the test cases. I'll show that in a moment. You select the test cases, power on the DUT, then run the test cases, and a log file and a trace file will be created for each test case. So the process for running the tests is very similar to what it would be for PCI Express compliance testing or NVMe compliance or conformance testing. What happens if you have a U.2 device or an M.2 device? From a protocol perspective, these are basically the same, so we can use an adapter. So you take the U.2 device and plug it in the adapter as shown on the slide here. This is the same method PCI SIG uses for PCI Express compliance testing. And if you had an M.2 device, I haven't seen any M.2 management interface devices yet. I have seen both CHEM and U.2 though, so we can use the adapter and that should be just fine. Dual port device, a little different. So if it's a dual port device, it has two separate PCI Express links. It requires two analyzers if you want to look at those simultaneously, but compliance testing has to be done on port A and port B independently. Now if you think about this, is compliance testing for PCI Express and for NVMe. For NVMe MI, it may be that it only is run on one of those. So I still to see any dual port U.2 NVMe MI capable devices. So that's still TBD how that would need to be tested. But in principle, the protocol is the same and that they would be tested in the same way. So what does the software look like to do this? So when you're running the NVMe MI conformance tests, you would select the appropriate test group, and you'll see there's two different groups, one for NVMe MI over SM bus and the other one for NVMe MI over vendor-defined message, which is the PCI Express vendor-defined messages. So when you select that group, then you can select which tests are desired to be run. You can choose the informational tests and the mandatory tests if necessary. There's a total of, I think, 60 tests here. Once you press apply on that, it's going to load them into the software, and then just select the run all button. You'll see the tests are listed on the left side. They're the ones that are going to be run. And on the right side, what's going to happen when the tests are run is you're going to see a log file generated. The first part of the test does some analysis of the device as to what its capabilities are and some initialization of the device. And then the second part of the log file is where it shows the results from the actual test case itself, which assertions it covered. This shows the initialization and then what the expectations of the test are. So these log files can be saved, and what will also be saved is a trace file of the test case. So when you need to debug it, then you can load up the trace file and see what happens. If you wanted to create your own scripts to be able to run the test, so the conformance tests themselves are encrypted and locked, so they're fixed to maintain consistency for the testing, but you can create your own both SM bus and PCI Express vendor-defined message test cases or exerciser scripts using the same hardware. So you can create SM bus packets, which are MCTP commands or NVMe MI commands. This is what the exerciser GUI looks like. You can see this, in this case, it would be creating an SM bus MCTP header packet. And the fields you can see on the right side are defined for the packet that's being sent. This is just a close-up of what the script looks like. So you can create a trainer script that does either SM bus as the first example there, or basically the same message being sent out over a PCI Express vendor-defined message. Remember, these MCTP and NVMe MI commands are higher layer than the physical medium. And the compliance testing is based around scripts that look like this. So to analyze the trace files, you're going to see an analyzer trace created for each of the conformance tests, or if you run an exerciser script. You would select the MCTP level decode in the analyzer software, and that would show you what the decode of these SM bus packets or the PCI Express vendor-defined message packets are. So you should see also the speed of the SM bus, that it's an MCTP packet, and then it'll decode the MCTP header. And if it's an NVMe MI command, then it would also decode the payload of the MCTP header into NVMe MI traffic. So this basically says that you have an SM bus command here. If you don't see this, you may have, it may be that it's not an MCTP command if you don't see this header, or it's MCTP traffic that's not an NVMe MI command. An example here, this is a trace which captured both PCI Express vendor-defined messages and SM bus based NVMe or MCTP packets. You can see the same commands which are created for each of them, but using a different medium in each time. But like I said before, the MCTP part of it is a higher level than the physical layer. If you want to trigger on these events, if you're trying to debug this and you want to find out when an event happens, then you can trigger on an SM bus event in the analyzer in addition to the PCI Express traffic. So for example, you have some traffic going on and an error happens on the device, but you want to trigger on the management interface and reporting that error. Then you could do that by setting a trigger on either the PCI Express vendor-defined message or the SM bus packet. So these are the layouts for SM bus packets or PCI Express vendor-defined message packets if you want to look for a specific case happening in a real situation. This is just a layout of what it looks like from a logical perspective, where you have a host, maybe a PCI Express switch, then a dual port interposer if it's two devices, and then looking at both ports at the same time, you would need two analyzers. So this only happens with the dual port on a U.2 device. If you want more information on this, the datasheet is available from our website that has all the configurations for the analyzer, the exerciser, the test platform, and the software, and it also has a list of the tests. As I mentioned before, if you want the details on the tests, those are available through the Interoperability and Compliance Committee or through UNH. One question here is, are the tests available today? Yes, the tests are available inside our software, which is on our website, teledyne-LeCroy.com. Another question is, where do I get the tests? Yeah, that's from our website. Another question here is, is it possible to simulate and send VDM messages via in-band? So using the exerciser, you can create PCI Express vendor-defined messages to test a device on the PCI Express link or on the SM bus. So yes is the answer to that. So a question, can you please explain how PCIe vendor-defined messages are sent from the host processor? So those are sent as controlled by software, but through the PCI Express link as TLPs. And another question is the availability of the material here. We will have this posted on our website within a few days, so that will be available. So good few questions there. So that's basically it for the webinar today. I just wanted to just call out the references to the specifications I talked about here. The NVMe specifications are available from the nvmexpress.org. PCI SIG provides the PCI Express specifications, and DTMF provides the MCTP specifications mentioned here. So these are all available on the website. I'd just like to say thank you very much for attending the webinar today. I hope this was useful for you. If you have any further questions, please feel free to reach out at psgsupport@teledyne-LeCroy.com, and we'd be more than happy to answer those questions for you. Thank you again. Have a great day, and talk to you soon. Bye.